Hello my scholars, this is my school YouTube channel and my name is Frank. In today's video we shall be discussing about simple alternating current. So relax, do not go anywhere, I will be right back. You are welcome back to my school YouTube channel. Like I said earlier, in today's video we shall be discussing about simple alternating current. But before we begin our lesson, let's quickly run through the objective of today's video lesson. So objective number 1, explain the peak and r.m.s values of current and PD. Establish the phase relationship between current and PD in an AC circuit. Explain reactance and impedance. Then determine currents in circuit containing A, resistance and inductance, B, resistance and impedance, and C, resistance, inductance, and capacitance. Then the last but not the least, determine power in an AC circuit. So let's begin with the lesson. So basically here we are going to be looking at the meaning of simple alternating current. Okay, so simple alternating current is one that varies periodically with time, both in magnitude and direction. So it's as simple as that. A current that varies periodically with time in both magnitude and direction is what's referred to as alternating current. Okay, so alternating currents are produced by time-dependent alternating voltages, and then we define AC circuits, that is alternating current circuits, as circuits through which alternating current flows. Okay, so an AC current is represented by this expression: I is equals to I naught sine omega t. Okay, and omega is equals to 2 pi f. So in this expression, anywhere we see omega, we replace it with 2 pi f, so that I becomes I naught sine 2 pi ft. Okay, so each of these terms, let us interpret what they mean. Okay, so I represents instantaneous current at a time t, while I naught represents maximum, or you can also call it peak value of current, while omega represents angular velocity, then omega t represents phase angle of the current. So similarly, we can as well still write this expression in terms of voltage. Okay, so similarly, an alternating voltage is represented by V is equals to V naught sine omega t. Okay, but remember omega is 2 pi f. So in place of omega, we replace it with 2 pi f, so that V becomes V naught sine 2 pi ft. Okay, now remember V represents instantaneous velocity at a time t, while V naught represents the maximum or peak value of the current. Then omega, we already know what omega represents. F represents frequency, we all know that y t represents time. Okay, so but if you are curious as to how this formula came about, then you can refer to our previous video on electromagnetic field part 2. You will see everything there. Okay, so let's move to the next slide. So here is just the graphical representation of AC current. Okay, so the first graph here is the graph of current against time. So this is the graph of the current. Sometimes you can also call it the waveform. Okay, then this is for B is voltage against time. So this is also the graph that is obtained. While for C, we also have I or V against time, and I and V in this case are they have the same frequency. Okay, so that the graph, both the graph begins at the origin or begins at point 0. So let's move to the next slide. Then we also have D, which is I or V against T. I and V of the same frequency, but in this case they are in phase of step. So this is just the graph. Okay, but so if you check this very well, you discover that the two graph didn't start, begins at the origin. And the reason for that is because the voltage and the frequency are in phase, okay, or they are in steps. So in this case, in that case, this is the graph you obtain. Now let's talk about peak and root mean square. Okay, r.m.s for short. Okay, so peak and root mean square values of alternating current and voltage. So basically we are going to be defining them, saying what they actually means. Okay, so the peak value of an alternating current is the maximum numerical value of the current. It's as easy as that. The maximum numerical value of the current is referred to as the peak value of an alternating current. Okay, so it is also known as the amplitude value of the current. Okay, similarly, the peak value of an alternating voltage is the maximum numerical value of the voltage. It is also known as the amplitude value of the voltage. Let's move to the next slide. Then on the other hand, since the alternating current and voltage are quantities which vary either positively or negatively, the root mean square r.m.s value is the most useful way to describe them. Okay, the root mean square value of current is the effective value of the current. Okay, also the root mean square value of voltage is the effective value of the voltage. But the root mean square value of an alternating current is defined as that value of steady, in bracket, direct current, which will dissipate heat at the same rate in a given resistance. It is given by r.m.s is equals to I naught over root 2. Okay, of course, I naught here is 1 I naught. So 1 divided by root 2, that will be equals to 0.701, then I naught. So that I.r.m.x, okay, is also equals to 0.701 I naught. So you can use either of these two. They are the same thing. So I.r.m.s here represent the root mean square value of the alternating current, while I naught, like we said earlier, represent the peak or maximum value of alternating current. So similarly for that of alternating voltage, V.r.m.x is equals to V naught over root 2. Of course, 1 divided by root 2, that will be equals to 0.707 V naught. Okay, so that V.r.m.s is also equals to 0.707 V naught. Okay, now let's talk about phase. Okay, so phase is the state of vibration of a periodically varying system at a particular time. The state of vibration of a periodically varying system at a particular time is what is referred to as phase. So let's move to the next slide to continue with our lesson. So now we are going to discuss about resistance in AC circuit. So this part is very, very important and it's worth taking note of. Okay, so this is the diagram of a voltage, okay, of an AC voltage connected across a resistor. This is exactly what you are seeing on the screen. So when an AC voltage is connected across a resistor as shown, the current I through the resistor and the voltage V across it at any instant in time are in phase or step with each other. So this is also worth taking note of, that whenever an AC current is connected across a resistor, the current and the voltage are in phase, or you can use the word they are in step with each other. That is, both of them attain their maximum, zero and minimum value at the same instant in time. So basically that's what we mean by in phase or in step. So this is the graphical representation of an AC voltage that is connected across a resistor. Okay, and this is the vector diagram. Okay, so let's move to the next slide. From Ohm's law, we know that V is equals to IR. So here we can make I the subject of formula by simply dividing both sides by R. So that I now becomes V all over R. Okay, but remember that V is equals to V naught sine omega t. Therefore, I is equals to V all over R. So in place of V, we replace it with V naught sine omega t. If we replace it, we'll be having I to be equals to V naught sine omega t all over R, right? And this will be equals to I naught sine omega t. Of course, remember that I is equals to I naught sine omega t, right? So this and this are also equal, since this is equal to this and this is equals to this. So this is also equal to this. So just take note of it, okay? So the voltmeter and ammeter connected in the circuit actually read the r.m.s values of voltage and current. Therefore, we can write that I r.m.s is equals to V r.m.s all over R. Okay, now let's talk about capacitance in AC circuit. Okay, so here this is an AC voltage that is connected to a capacitance. So this is the diagram. Now let's move to the next slide. So when an AC voltage is connected across a capacitor as shown, as was seen in the previous slide, the current I in the circuit and the voltage V across the capacitor are out of phase. Okay, so they are out of phase in this case, not in step. So out of phase simply means that they are not in steps. So in this case, the current is set to lead on the voltage. That is, the current is ahead of the voltage, and the voltage is set to lag on the current. That is, the voltage is behind the current. So the phase difference between the current and the voltage in this case is 90 degrees or pi over 2 radians. Now remember that 90 degrees is equivalent to pi over 2 radian. Okay, that is, the current leads the voltage by pi over 2 radian. So given that V is equals to V naught sine omega t, then I is equals to I naught sine bracket open omega t plus pi over 2 bracket close. And the reason for that is because in this case the current is leading the voltage by pi all over 2. Okay, so this is the graphical representation, okay, of when an AC voltage is connected across a capacitor. Okay, so let's move to the next slide. Now, this is the vector diagram. So as you can see in the vector diagram, the current, okay, leads the voltage by 90 degrees or pi over 2. Okay, so IC here is equals to current in an AC circuit with capacitance C, while VC is equals to voltage in an AC circuit with capacitance C. So the capacitance opposes the flow of current. This opposition to the flow of alternating current offered by the capacitor is known as capacitive reactance, and it is represented by XC. So take note of this, okay? And XC is given by, or mathematically, SC is expressed as 1 over omega C. But remember, we said earlier that omega is equal to 2 pi f. So in place of omega, we replace it with 2 pi f, so that XC is now equals to 1 over 2 pi FC. But remember that XC is called capacitive reactance. That is the opposition offered, okay, to the flow of alternating current by the capacitor. So now let's interpret what each of these parameters represent. So omega here is equals to angular speed of the alternating current, F is equals to frequency of the alternating current, and C is equals to capacitance of the capacitor. So let's move to the next slide. Now from Ohm's law relationship, okay, Ohm's law relationship also applies to this circuit. And remember that V is equals to IXC. Now remember that IXC here is not acting as a resistance, because it's actually the resistance that is offered to the flow of alternating current by the capacitor. Okay, so here if we decide to make if we make I the subject of formula, then I becomes V all over XC. Okay, then but remember that in this circuit, the voltage, okay, the voltmeter and the ammeter measure r.m.s value of current and voltage. So remember that. Therefore, r.m.s is equals to V r.m.s all over XC. Okay, so this is the graphical representation of XC against F. Okay, so from this graph we can see that as the frequency increases, the XC decreases, or vice versa. Okay, so what this simply means is that this XC only allows high frequency current, okay, to flow through, but blocks low frequency current. Okay, so the unit of XC is ohms because it's resistance, but this resistance is the one offered by a capacitor and not by a resistor. Okay, so basically both of them are the same. Okay, so the unit of XC or capacitive reactance is ohms and represented with this symbol. So let's move to the next slide. Now let's talk about inductors in AC circuit. So this is the diagram of an AC voltage connected across an inductor. Okay, so when an AC voltage is connected across an inductor as shown, the induced EMF in the inductor opposes the change in the current. This makes the current to delay behind the voltage in the circuit. The current is set to lag behind the voltage. The phase difference between the current and the voltage is 90 degrees or pi over 2 radian. That is, the current lags behind the voltage by pi over 2 radian. So this is just like the opposite of capacitor in AC circuit, right? In capacitor in AC circuit, the current leads, right? But in the case of inductors in AC circuit, the current lags behind. So just note the difference. So given that V is equals to V naught sine omega t, then I is equals to I naught sine in bracket omega t minus pi over 2. The reason is because in this case, the current lags behind the voltage by 90 degrees. And remember that 90 degrees is equivalent to pi over 2 radian. Okay, so let's move to the next slide. Now, this is the graphical representation, okay, of inductors in an AC circuit. This is the vector representation, right, where VL is equals to voltage in an AC circuit with inductors L. Let's move to the next slide. While the opposition to the flow of alternating current offered by the inductor is known as inductive reactance, and it is represented by XL, right? So mathematically, SL is equals to omega L, right? But omega is equals to 2 pi F. So in place of omega, we replace it with 2 pi F, so that inductive reactance SL is equals to 2 pi FL, right? Where F here is equals to frequency of the AC or alternating current, L is equals to inductance of the inductor, W is equals to angular speed of the alternating current. Ohm's law relation also applies to this circuit, such that we know that V is equals to IXL, right? Because now we are now applying Ohm's law to this circuit. So in place of arrow, we have to replace it with XL, because this is the resistance offered by the inductor. Okay, so if we make I the subject of formula here, I becomes V all over XL. Okay, so to make I the subject of formula here, we simply divide both sides by XL, right? So if we do that, I, which is current, is now equals to V all over SL. But remember what we measure, okay, in this circuit using voltmeter and ammeter is r.m.s values of I and V. So that I r.m.s is equals to V r.m.s all over SL. So this is the graphical representation, okay, of SL against F, as you can see, okay. So here, as the frequency increases, the frequency of the AC current increases, also the resistance offered by the inductor also increases. So the unit of SL or inductive reactance is ohms, okay, represented with this symbol. So let's move to the next slide. So on the next slide there are just some examples for us to apply some of all those formulas we have seen, okay, apply them to solve some problems. So let's begin with question 1. Calculate the reactance of the inductor in the circuit diagram below. Here we are asked to take pi to be equals to 22 all over 7. So you can see in the diagram, the value of L is given to us to be 0.7 H, that is, H is Henry, okay, the unit of inductance is Henry, right? Remember that this is the symbol of inductance, so take note of this. So 50 ohms represent the resistor, okay, and not, or represent the resistance and not frequency, okay. So the frequency here is given to us as 60 Hz, okay, so just take note of that. This is This symbol here you are seeing here represents a resistor and not frequency. Okay, so let's move over to the board to provide answer to this question. So in this question, basically we already know that L is equals to 0.7 Henry. Okay, and here again we are given R to be equals to 50 ohms. We are given voltage to be equals to 230 volts. And we're also given frequency to be equals to 60 hertz, right? But remember, in this question, we are asked to calculate the reactance of the inductor. And we know that reactance of the inductor SL is given as omega L, right? And remember that omega is equals to 2 pi fl, so that our SL equals to 2 pi fl, right? So the next step is just to substitute the values that are given to us. So for this question, we only need frequency and L, so we don't need resistor, or we don't need the value of resistance, and we don't need voltage. Okay, so let's substitute it. So SL will now be equals to 2 times 22 all over 7. That was what we are told to use in the question. Then times frequency is 60. Then times L is 0.7. So 0.7 we can write it as 0.7. We can write it as 7 over 10. These two are the same. So here let's use 7 over 10 so that it will be easy for us to cancel out. So you'll be having 7 all over 10. Okay, so 10 here is going to cancel out 10 here to give us 6, right? Then 7 we cancel out 7 here. So that we'll be having 44 times 6. And this will be equals to 264 ohms, right? Since we are talking about resistance offered by the inductor. Okay, so this is the value of the inductive reactance, okay, that we are asked to calculate for this question. So let's return back to the screen to continue with the other examples. So let's solve question B. A capacitor of capacitance 4 microfarad was used in a radio circuit connected to a 50 Hz AC source. Calculate its reactance. So here we are asked to take pi to be equals to 3.14. So let's move back to the board to provide answer to this question. So here in this question we are asked to calculate capacitive reactance, okay, for this question. So we are given pi to be equals to 3.14. Let's just write out the parameters that are given to us. We are given the capacitor of the capacitance, okay? So let's call it C to be equals to 4 microfarad, which is equals to 4 times 10 raised to the power minus 6 farad. Okay, take note of that. Then we are also given frequency to be equals to 50 Hz, right? But remember that capacitive reactance XC is equals to 1 all over omega C. But remember, omega C is equals to 2 pi F. So here we just put C, right? So next, we substitute the values to get our answer. So you'll be having 1 all over, so 2 times 3.14, then times 4 times 10 raised to the power minus 6, okay? Then, okay, let's fix in our frequency first, the value of frequency, which is 50, then times 4 times 10 raised to the power minus 6. Okay, so this is what we have. So if we multiply everything here, okay, so if we multiply the denominators, right, and divide it by 1, we'll be having approximately equals to 7.96 times 10 raised to the power 2 ohms. Okay, so this is what the resulting answer is going to be. Okay, 7.96 times 10 raised to the power 2 ohms. So this is the value of the capacitive reactance. Okay, so let's return back to the screen to continue with the other examples. So example 3, calculate the peak value that could be obtained from a 220 V r.m.s main supply. Okay, so to provide answer to this question, we'll have to return back to the board to do just that. Okay, remember that we said V is equals to V naught, that is V r.m.s is equals to V naught all over root 2. right? So in this question, we are asked to calculate for V naught, which is the peak or maximum value of the voltage. So that V naught is equals to V arrow mx value of the voltage then times root 2. Okay, so here we are given this value V arrow ms value to be equals to 220, right? So we just plug it in here. So that V naught, that is the peak voltage, is equals to 220 times root 2. Okay, and this will be equals to 311.1 volts, right? Since we are talking about voltage. So this is the value of the peak voltage. Okay, so let's return back to the screen. So this is where we bring the preview of today's video to a close, but you can watch the complete video by simply clicking on the link in the description below, and that will take you to my school website. There you will have to subscribe to enjoy the complete video. So in the complete video, you will learn about reactance in r.m.s series circuit. You also learn about power in an AC circuit and many more. So I believe you enjoyed the preview of the video that you just watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we release the next video.